Hey guys, so we're going to talk about how we're going to add vectors algebraically. There are quite a few examples in this section, and this video is going to be fairly long. Please feel free to break it up. I will actually push back the assignment because of how long this lecture is going to be. But please also attend Google Meets if you need help with anything. Here we go. So, adding vectors algebraically is a super useful tool because we're not always just heading in one direction. We don't always have things that are going like straight in a perfect line. But there's a lot of different ways that we can do this. We actually skipped a section on drawing scale diagrams because, as this first bullet point said, it's not a great use of our time. We want to be more efficient. So we still want to draw our vectors and the directions accurately, which is why we went through that first section. But we need to have a better way of finding the resultant, and that is math. So your resultant is just the vector that goes from your very beginning, where like the object's motion first started, to where the object's motion ended up. So we have three different things that we're going to be looking at. Our perpendicular vectors, where we form a 90-degree angle, non-perpendicular, where we don't, and then we have three or more vectors that we need to add together. So if we have two vectors that need to be added together, and we have a perpendicular section, then we can draw the vectors and use the Pythagorean theorem or trig ratios. And remember, every single vector that we find the resultant of needs to have a magnitude and a direction. So there's more steps than just solving a trig function here. We actually have to make sure that we have a direction. Usually it's going to be lined up with north, south, east, or west, and make those kind of complicated combinations of directions there. So first example, Neil walks 1,500 meters north. Oh, what? And okay, so he walks 1,500 meters north, and then he's going to walk 750 meters west from the planetarium. We're going to find his total displacement, including the direction. So what we're solving for is that resultant right there from where he started to where he finished. Now we know that he went north and then directly west. So this is forming a 90-degree angle, which makes our lives much easier. So in this case, what we're going to use is the Pythagorean theorem to solve for how long that green line or that resultant line is. So a squared plus b squared equals c squared. Doesn't matter which one you put in for a or b. So 750 squared plus 1,500 squared equals c squared. It comes out to like a super big number, and then you take the square root. So I get 2,812,500. I'm going to square root that, and my resultant vector c is 1,677 meters. So that's what this side is. So I have my magnitude. Now I need to find my direction. How in the world am I going to do that? We're going to use trig. Yay! So what I need to figure out is what direction that vector is heading. So I'm going to find this angle right here, and I have all of my sides, so I can use pretty much any trig that I want to, but I'm going to go ahead and use tangent because it's using the two numbers that I didn't solve for myself. So that means that even if I got 1677 wrong, I could still get my direction correct. So tangent of theta equals my opposite over my adjacent. So 750 divided by 1,500. And I'm going to use the inverse tangent to solve for theta. And theta, I believe, is like 26.6 degrees. Oops, 26.6 degrees. So I have to decide how I'm writing that fully out in my direction. So my resultant vector, the way that he went for his final displacement, is 1,677 meters. And we went north, then 26.6 degrees west. Next slide. So here's all of that written out. If you wanted to follow their work, they rounded. I don't appreciate that. That's fine. So now we're going to go through an example of adding non-perpendicular vectors. So we need to make sure that we are really digging deep in these. It's like solving a big puzzle. This next example is going to take us a little bit, so please bear with me. But when you have two vectors that you're adding together that do not have a 90-degree angle in them, we need to draw everything out, draw all of the angles in that we can figure out, and then we're going to realize that the three vectors form a triangle. Since the original two vectors are not perpendicular, we can't use the Pythagorean theorem, so we're going to be using our law of sines and our law of cosines. So please make sure if you don't have those written down, you go back to the trig video and get those written down. And we need to solve for the missing magnitude and the direction of that resultant. So a couple quick review things that we didn't cover in the trig video but are going to be very important. Remember that a straight line is 180 degrees. Also, every single angle within a triangle equals 180 degrees. Right angle is at 90, but then also I'm going to draw in color code this little section right here. I highly suggest you do this on your notes as well. So this is two parallel lines that are intersected by another line. And what this is going to be able to tell us is what angles are equal to each other. This is going to be extremely important. So alternate interior, exterior angle rules and all that sort of stuff. I'm going to be honest, I don't remember the exact math term, but these two angles are always going to be the same, which means that to add up to 180, the outside angles are always going to match up as well. And these are only when our two lines are parallel to each other. And then the exterior angles and the interior angles here are also the same. And this is only when we have two parallel lines that are intersected can we fully make these claims that all these angles are going to be the same as each other. Alternate interior and exterior angle theorem, I think. I don't remember. Okay, so this example is going to take us a little bit, so please bear with me. Erwin is carrying his cat around for a walk, and that's how we know this is going to be a problem, because that's weird. He walks 25 meters west, 15 degrees north, then 110 meters south, 40 degrees east. Find his total displacement. So I'm going to draw this out for you. And what we're going to do is we're going to start with our coordinate planes or our compass roses so that we have a really good idea of what direction everything is heading in, and we have something to compare it back to. So for this first part, we're going 25 meters. We're heading west and then 15 degrees north. So we're going to say that's 25 and this is 15 degrees. Then I'm going to set up a second compass rose. And its origin is going to be right where that line ended, because that's where my next line is going to begin. And he's heading 110 meters south, 40 degrees east. Now we don't have to draw this out perfectly lengthwise, making sure it's all measured correctly. But we do need to have a really great approximation of how long this line should be. Otherwise, we're going to get completely thrown off. So this 110 meters is going to be about 4 times as long as that 25 meter line. And the reason we have to be careful of that, I'll show you in just a second. But we're going to be going south, but then 40 degrees east. So something like this. I'm just going to stop right there because that's long enough. So the thing is, if I would have stopped, I don't know, maybe right here, it would have looked like I was going, it would have looked like I was going 90 degrees for my resultant, and that's just not right. So we want to make sure that we are drawing the line fairly accurately out the direction that it needs to go so that we can see everything. So this is 110 meters. Notice mine still isn't 4 times the length, but I get the idea of where it's going. And this angle right here is 40 degrees between myself and my line. So what I'm solving for is that's the line, a magnitude and direction of this guy. So there's a whole heck of a lot going on in here. I have several different angles that I don't know, like what that whole angle of that triangle is. Also, what just this angle of my resultant vector is. I don't know this guy. I don't know if I need to know it yet, but I should probably figure that out. I also need to know what this guy is, and then I still need to figure out what that whole magnitude is. So we've got a lot going on. So I'm going to go to the next slide where it's actually like drawn out nicer. So the first thing that I'm going to go ahead and do is I'm going to solve for theta. So the first thing I'm going to do here is I'm actually going to go ahead and solve for theta. And the reason I'm going to do that is because I have this 90 degrees right here. And I already know what this angle is. And then based on my alternate angles from my perpendicular lines, I know that that one right there, not perpendicular, parallel lines, I know that that angle right there is also going to be 15 degrees. So this is like the easiest math I can do right now. So I'm going to take 90 degrees from that compass rose angle is equal to 40 plus 15 plus my theta. So I solve that and get that theta equals 35 degrees. Oops. So theta is 35. Sorry if that's really hard to read on your screen. Let me go ahead and rewrite that. We'll just put it in black. Theta is 35. Still hard to read. Hopefully you wrote that down on your paper. Okay. So now from there, I have this. Oh, wrong button. This one. I have the length of this line, and I have the length of this line. So I have 2 lines and 1 angle on my triangle. What's great about the angle that I have right now is it's opposite the side length that I need to solve for. And when it's opposite of that side length, I can use my law of cosines to go through and figure out the magnitude of that side length. So again, make sure you have that written down somewhere. I'm going to flip to the next slide. It's going to look a little complicated, but it's just the law of cosines and filling things in. So my resultant line, magnitude squared, equals my first magnitude squared plus my second magnitude squared, minus 2 times my direction 1, my direction 2, times that cosine of theta, which was opposite of where the missing line is. So when I plug all of this in, got the math right up here for you, I get that my resultant is 90.66 meters. So I can go back here and say, okay, I know that this is 90.66 meters. Now what? Now I have to solve for the direction that it's heading in because I have my magnitude, but I need my direction. So to do that, I have all 3 side lengths, and I have 1 angle. So I can go ahead and actually solve for my other angles. Now, I don't care at all about this one down here. That's why it's not labeled. It's not going to give me any new information. So what I want to do instead is actually solve for this angle up here of my triangle. And the reason I'm solving that is because eventually I want to get this guy, which is just telling me what direction my resultant vector is heading. So I'm going to use my law of sines because I have an angle that I'm trying to solve. I know 1 angle and I know all of my sides. So what I'm going to do is I'm going to set up my 35 degrees that I already know goes with my resultant vector. So sine of 35 divided by that 90.66 is going to equal the sine of my alpha divided by the side length opposite it, so 110. So you can cross multiply and get 110 sine of 35 equals 90.66 sine of alpha. Divide both sides by 90.66. And then I would take my inverse sine of this whole guy. Sorry, I ran out of room. I can't rewrite it. And that's going to give me what my angle alpha is. So actually, I'm just going to jump ahead to where that's written out much nicer. So what I'm going to get then is that alpha is 44 degrees. Now, let's be real here. This is weird. And this is one of those examples that is given to you because it's a weird example. But obviously, this whole purple angle right here is much bigger than 44 degrees. Much bigger. So what in the world is happening? Well, you have to remember that when you're doing trig, you're actually always getting two answers in a way, but it's just going to give you one of them. So this 44 degrees is part of a line. So if we have a line, we have, maybe it's, oh gosh, okay, hold on, let's do it this way. So we have like a 44 degrees here, or we have the whole thing without that 44 degrees. It's a weird example, but it's so that we can show you this and get it kind of out of the way. So if the 44 degrees doesn't make any sense, which it doesn't, what I'm going to do is I'm actually going to take my 180 from my straight line and subtract the 44 degrees to see what the rest of that line is to make sense. So I have my 44 degree angle, or I have the angle that forms the rest of the line. 136 makes a whole lot more sense, and it fits in with everything else that we did. So now I'm going to go through, and I know this is getting complicated. Let's go ahead and erase this. So I know, oh, no, just kidding. I know what my alpha is, and my alpha includes this 15 and this beta. So I take my alpha minus the 15 and minus the 90 degrees that's formed here, and I'm going to get my beta. It's a long example. So it's going to show me that I'm going 31 degrees in that direction. So my resultant angle is heading 31 degrees that way, which means I'm going mostly south, but then 31 degrees east. So I finally have everything I need. Yay, trig. However, there are other ways that are also mathematically helpful. So let's go and get to our component vectors. So when we're adding 3 or more vectors on this example, we want to actually use the components. So in every triangle, we have a horizontal line and a vertical line, and they're attached by some line at an angle. Well, all that we've been doing so far is taking this line and finding what this line is. So now we're kind of going backwards and breaking it down into the horizontal and the vertical components. So that's when we're going to really use our trig again, and you're going to see a pattern really fast that's going to pop up. Just talked about that. So every vector, we are now going to start writing the components as having an x component and a y component. So your x is your horizontal and y is your vertical. So if we're looking at vector 3, the horizontal component, or the direction that we're going horizontally, is going to be vector 3x. And then the vertical, or how far it's going up and down, is going to be vector 3y. So we're going to go through these examples. I'm going to go ahead and write out my components of these vectors. So I need to figure out where I'm going. I'm going 75 meters per second, north 36 degrees east. So I'm going mostly north. I'm going 36 degrees towards the east. So this angle right here is 36, and I know that this is 75 meters per second. So I have my y component and my x component. So I need to figure out how I'm going to solve for each of these. So for my vector in the y direction, I have my angle. I'm looking for y, so I can use my adjacent and my hypotenuse. So I'm going to use cosine of 36 degrees equals, I don't know what that line was for, equals my adjacent, so my y, divided by my 75 meters per second. So my vector in my y, I think this is incorrect actually in the slides. So there's that. Cosine of 36 degrees times my 75. It's going to give me 60.7 meters per second, and my y direction is heading north. So then let's go and solve for the x. So my vector in my x direction, I'm going to try to only use the numbers that they provided me so I can make sure I get at least one part of the problem right. So I'm going to have sine of 36 equals my x component divided by 75. So sine of 36 times 75 is 44.1 meters per second, because I'm carrying the units from my original vector, and this guy is heading east. So those are my two components that I have for that first problem. Now let's do part B. That one, okay. So part B. I'm going 4.3 kilometers south, then 18 degrees west. So I start heading this way, but I veer off about 18 degrees. 18 degrees, and it's 4.3 kilometers. So I have my y component and my x component of that line. That should form a 90-degree angle. Okay, so if I'm going to go for a y, my vector in the y direction, you could label as by if you wanted to, since it's technically vector b. It's going to be the cosine of 18 degrees equals y divided by 4.3. Cosine of 18 times 4.3. It's going to give me 4.1, and that's going to be kilometers, and it's heading south because that's the direction that my vector is going. And then if I solve for my x, it's going to be the sine of 18 degrees equals x divided by 4.3. And that's going to be 1.33 kilometers, and that direction is heading west. So those are my components of those two. So once we have those, if we were, say, doing both A and B as like one path that we were heading on, we could actually take the vectors in the x direction and add them together, take the vectors in the y direction and add them together. And then what we actually we're going to end up with is a triangle that we can solve for the resultant very easily. So we would use the Pythagorean theorem and trig ratios, because what I can do is I can take all of my y's, and let's say like they stopped there, but I added, like part 1 stopped there, but I added part 2 together with it, and I can take all of my x's, and maybe the first one stopped there, but the second one goes all the way to here, and then I have one triangle with a 90-degree angle and a resultant. So I can then use my Pythagorean theorem and my trig ratios to find everything about that, which is much simpler. So a horse in a pasture is traveling 55 meters west, then 25 meters south, then 67 meters south, 17 degrees west, then 13 meters. Okay, you get it. Find the horse's total displacement using the component method. So I'm going to go piece by piece. So the first thing we're doing, I'm going to call this, like, this is part A, B, C, D, E, okay. And I'm just going to add all of the things I have over onto the side once I solve for them. So in vector A, I'm heading west, which is just in x direction. So vector A in the x direction is 55 meters west. I don't have to do any math there. Look at that. That's nice. Then vector B is going south, so it's going in the y direction. And that's 25 meters south. Vector C then gets complicated. So vector C, I'm going south and 17 degrees west. So south and a little bit west. So that's 17 degrees right there. And it's 67 degrees. So I'm going to take and solve for both my x and my y components of my triangle. So let's do the y component first, is going to be cosine of 17 equals my y divided by 67. So that's going to be cosine of 17 times 67, 64.1 meters, and in the y direction I'm heading south. Then my vector in the x direction is the sine of 17 equals x divided by 67. So my vector of c in the x direction equals sine of 17 times 67, 19.6 meters, and that guy is heading west. Okay, so now I've got all that done. Vector D, I need to break into components as well. Oh, pen. Purple, of course, because why? So vector D, I'm going 13 meters, but I'm going north and then 33 degrees east. So that's 33, and this guy is 13 meters. So my vector D in the x direction is sine of 33 equals x divided by 13, and my vector of D in the y direction is the cosine of 33 equals y divided by 13. So I ran out of room there a little bit. So vector of d in the x is sine of 33, 7.1 meters. And in the x direction, I'm going east. And then for y, it's the cosine. So that's 10.9 meters, and I'm going north. Okay, almost there. One last one. So now, for part E, I'm going 24 meters north, then 29 degrees west. 29 degrees, and it's going 24 meters that way. So my vector E in the x direction is the sine of 29 equals x divided by 24. And my vector of E in the y direction is cosine of 29 equals my y divided by 24. So I have almost no room. My vector of E in the x equals sine of 29 times 24, 11.6 meters west. And my vector of E in the y direction is, we'll just say 21 meters north. Okay. I got my components. Yay. But now what I have to do is actually figure out my total displacement. And what that means is I need to go back and I need to add all of my vectors in the x direction. So I've got my 55, and that's going west. Then I've got 19.6, and that's going west. I'm just writing the directions with them so I make sure I have all my positive and negative, because my next one is actually, if I was going to add it, it's 7.1, but it's going east. So what I need to do is make that negative. So that's going west. And then adding my final one, which is 11.6, and that's going west. So in the x direction, I went 55 plus 19.6 plus negative 7.1 plus 11.6. I'm going to write it over here, 79.1 meters west. Whew. Okay. Then the sum of my vectors in the y direction are going to be 25 south. And normally we would consider south negative, so I'm going to make that a negative north. Then plus 64.1, also going south, so I'm making it a negative north. Plus 10.9 north. Sorry if it's getting really crowded. Plus 21 north. So I'm going to add all those together. Negative 25 minus 64.1 plus 10.9, 0.9 plus 21. So I'm actually headed a negative 57.2 north, or a positive 57.2 south. Okay, almost there. So now I'm erasing all of this. Up to that. Okay. And what I can do with these is now create my final triangle. So in the x direction, I went 79.1 meters west. And in the y direction, (79.1 meters west), and then in the y direction, I went 57, 57.2 meters south. I'm trying to figure out now what the magnitude and direction of this resultant are. Yay! I know that this is 90 degrees, so I can use my Pythagorean theorem to solve for my final side. So c squared equals 79.1 squared plus 57.2 squared. And that's going to give me that this side here is 97.6 meters long. But now I need to figure out my angle. So I'm going to figure out if this is where my compass is. I'm going to figure out this internal guy right here. So if I'm solving for this theta, I'm going to use the two numbers that I already had. So my tangent of theta equals my opposite over my adjacent. So 57.2 over 79.1. So theta is going to be 57.2 divided by 79.1. Inverse tangent of that, I'm going to get 35.9 degrees. And what angle is that actually heading? Well, it's inside of this right here. So I'm going to be going west. So I ran out of space and almost colors. Okay, my answer, my resultant vector is 97.6 meters, and I was going west with a 36 degrees towards the south, because that's what this is telling me right here. Boom. So there's all of that. And there's your answer. All right, that was a long one, but I'm going to give you guys until Monday to get through that. We'll answer questions in class and do a work day in class on it. All right. Talk to you later.